So today we're going to be talking about objects in moving in simple harmonic motion or experiencing simple harmonic motion, and we want to calculate the displacement and the acceleration of such objects in the system. So we have an example, or we have the formula, which is Hooke's law. And Hooke's law states that the force, which is the spring force, is equal to the negative k, which is the constant, spring constant, times the x, which is the displacement of the object. So we're going to label these force, spring constant, and that's the displacement. So that's one formula, and that's the formula for the system and a spring, an object in a spring system. So we're going to put that up here, and that's force is equal to negative kx. So we have an example, and it says an archer applies a force of 52 newtons on a bowstring with the spring constant of 490 newton meters, or newtons over meters. What is the bowstring's displacement? So we know that the force is 52 newtons, and we know that the K is 490 newtons over meters, and we want to find the X, which is our displacement. So we can plug into the formula, so we have 52 newtons equals negative 490 x. So if you distribute the negative, you have 52 newtons equals negative 490 x. And then you divide each side by negative 490. And our displacement is going to equal negative 0.106, and that's going to be in meters because the newtons cross out. So it's going to be meters. So we have our displacement of this bow, or not the bow, but the bowstring's displacement, is negative 0.106. So now that we've done an object in a spring system, we can now move on to an object that is also in simple harmonic motion, but it's dealing with periods and frequency and all that fun stuff. So that is a period of a simple pendulum in a simple harmonic motion. And that equation is T, which is your period, is equal to 2 pi and the square root times the square root of the length divided by your acceleration due to gravity. So this is the formula you would use when you're trying to find either the period or the length or the acceleration of an object in a simple harmonic motion. So we're going to erase that, and we're going to put it in the corner, and that is T is equal to 2 pi times the square root over h. And now we're going to apply that to a problem, and it says on Mercury a pendulum 1.14 meters long would have a 3.55 second period. So let's calculate the acceleration of gravity for Mercury. So we know that the period is 3.55 seconds, and we know that the length of the object, or the pendulum, is 1.14 meters, and we want to find the acceleration. So We plug that in and we have 3.55 seconds equals 2 pi times the square root of 1.14 meters over AG. And we're trying to find our A. So we can divide both sides by 2 pi. And that gives us 0.56 equals the square root of 1.14 over AG. So now we're going to square, or not square root, but we're going to square both sides so we can get rid of the square root. That gives us 0.319 is equal to 1.14 over AG, and we're going to move that up here. So now we have 0.319 is equal to 1.14 AG. And now we know that if we can just switch them, it's going to be AG is going to equal 1.14 divided by 0.319. And our acceleration due to gravity on Mercury would be 3.57 meters per second squared. Oh, that's really, okay, we're going to write that again. Hold on. It's going to be, our acceleration is going to equal 3.57 meters per second. And that is how you use the period formula to calculate either the period, the length, or the acceleration due to gravity in a simple harmonic motion system.